Today we are going to talk about the exponential function. An exponential function can be written in the form of y equal a power of x and plus b. The independent variable of x can be any real number and is the exponent of a. A is what we call the base of the exponent. It is a positive number, but it cannot be equal to 1, or else the graph will just be a straight line. Lastly, b is the constant number. Let's first look at the graph of the exponential function and identify some major features. In this graph, when a more than 1 and x is negative, the exponential function is very flat, whereas when x is positive, the function rises rapidly. On the other hand, when a between the 1 and 0, the function is monotone decrease. It decreases rapidly when x is negative. However, when x is positive, the function becomes very flat. Both graphs intersect at the point of 0 and 1 plus b, and is symmetric about the y-axis. In addition, the curve approaches the x-axis but never touches. An exponential function's rate of change is based on the repeat multiplication, as opposed to the linear function, which is based on the repeat addition.
We will now conceptually explain the mathematical model of exponential functions. Firstly, we can use the increased exponential functions y equal to a to power of x, assuming a greater than 1, to analyze the relationship between temperature and the amount of ice cream sold. In this example, we can consider both first and second quadrant, as temperature can be negative in the winter. From the graph, we can know the amount of ice cream increase rapidly with the temperature rise. On the other hand, we also can use decreased exponential function y equal to a to power of x, assuming a greater than 0 but less than 1, to represent the relationship between the effectiveness of medicine and time. But in this example, we only consider first quadrant, as time can never be negative. From the graph, we can clearly see the effectiveness of medicine decreasing as time increases.
So how do we actually interpret the results from these graphs? In the ice cream example, we can conclude that when temperature rises, for example when we move from spring to summer, the quantity of ice cream sold increases as well. More importantly, the rate of change in ice cream sales is increasing as temperature rises, meaning that when it gets hotter and hotter, ice cream sales increase at a more rapid rate. This makes sense because the hotter it is, the more people will want ice cream, and conversely, not many people would want ice cream during winter seasons when it's already so cold. Therefore, an exponential relationship arises between the two variables, namely temperature and ice cream sales. Furthermore, in the second example, it can be concluded that as one takes the same medication over a long period of time, the effectiveness of the medication will decrease, because the body will slowly adapt to the continued presence of the medicine and eventually develop tolerance. Some people consume Panadol so frequently that over time, taking it no longer relieves the headache. So to get the same effect from the medicine, one may have to increase dosage or try other types of medication.
From this example, we can also identify some relevant social, environmental, or ethical concerns. In the ice cream example mentioned just now, knowing that ice cream quantity can change so drastically during seasonal changes, ice cream producers can forecast how much ice cream should be produced to minimize wastage and negative environmental impacts caused during the process of producing ice cream. On the other hand, in the diminishing effect of medicine example, ethical concerns are raised because doctors or pharmacists continue to charge high prices for medication regardless of how effective the medicine is, and this is especially unfair to those who cannot afford such prices. Therefore, not only do we see how exponential functions can be so relevant to us in real life, we can also identify the social, environmental, and ethical concerns that comes as a result.